Hello fam. In this video we're going to go over the most frequently asked questions from the quizzes for lesson 61, and then we are going to do lesson 62 part 2. So I'm going to say that one more time. In this video I'm going to go through some of the questions that I got from lesson 61 quizzes. And then we are going to do lesson 62, part 2. So, that being said, let's get going. Okay, so I'm going to switch over to my quizzes. And I'm going to look at the part 1 quizzes. So this has to do with this page in our notes. So specifically, we're referring to this picture here. And what we're trying to do here is make the connections between the normal curve and where we get a confidence interval from, or how a confidence interval was constructed. So I think that the first few questions are okay. So what are we estimating? What is our point estimate? What is the margin of error? So up here, what we should have is that our point estimate, so for us, our point estimate was 2295. Just kidding. 2505 is our point estimate. Well, that is the value that's in the center of our normal distribution. So your point estimate is this number that's in the center, 16.72. Then they want to know the margin of error. Well, on our picture here, the margin of error is 2 times your critical value, which we go through and figure out is 2 times 1.05, and the margin of error is what we add or subtract from our point estimate. So that means on this picture, our margin of error is this space. So coming back, that is 0.15. Construct a confidence interval with the sample data. So this one asks, what is your level of confidence? I think you should be able to figure that out from our notes. What is the critical value? Now this is the one that I think you guys are the most interested in. So if I refer back to my notes, the critical value in this sample or this example was 2. Well, where did we get that 2 from? Well, it's how far away in standard deviations we are from the mean. So if we're 2 standard deviations away from the mean, that is 95% of our data. That 2 comes from how many standard deviations away you are, and that is a z-score. So if we come back to this picture and it asks us what is the critical value, well, what this is trying to tell us is that if you're within 1.645 standard deviations of the mean, that's 90% of your data. So what is the critical value? 1.645. So this right here is telling you that if you're within 1.645 standard deviations of the mean, 90% of your samples will capture the true value, or will be within 1.645 standard deviations of the mean. Then from there, you calculate your lower and your upper bound, but make sure that you're careful because they're giving you your margin of error here. So when you do your lower bound, you don't have to know the standard error and you don't have to use critical value. I was just seeing if you knew where the critical value was on this image. So when you go to find your lower bound, you're doing 16.72, subtract 0.15. So your lower bound should be 16.57. So you take this center value, subtract your margin of error, center value, add your margin of error. Okay, 62, this is the other one where we had lots of questions. So I am going to turn to page 608 in my notes, and I'm going to write some things down there that have specifically to do with critical value and standard error. So this is page 609. I should have said this before, but if you don't feel like you need this information, then you are more than welcome to skip ahead. You do not have to be watching all of this. You can skip to the parts that you actually need. So the first one says, explain what will happen to the interval, the confidence interval, if our confidence level were increased to 0.99. So the first thing that I want to look at is some values on our pink table. So if I move from left to right, sorry, I'm just adjusting. I notice that my critical values get larger. So 90% gives a critical value of 1645. 95% gives a critical value of 1960. And 99% gives a critical value of 2.576. So as you increase confidence level, you also increase critical value. That is how we come up with what we're talking about here. The wider your intervals are, the more confident you are, your interval will capture the true mean. So wider intervals make you more confident. Why are those intervals wider? Because your critical value is bigger. So that means you're adding a bigger number to your point estimate. So we have this formula, point estimate plus or minus critical value times standard error. Okay, well, if all we look at is the confidence level, for 90%, which is what we start with, you take your point estimate plus or minus 1.645 times your standard error. If we increase it to 99%, that changes it to your point estimate plus or minus 2.576 times your standard error. Notice that your critical value gets bigger. So that means that your interval gets wider. That means that your interval gets wider. How would a 90% confidence interval based on a sample of 200 compare to the original, what am I thinking here, family? Confidence interval. Sorry about that. Okay, well, let's think about this. So, what is affected by sample size is your standard error. So, standard error is equal to your sigma, well, in this case, it's your SX over the root of your sample size. So we have our point estimate plus or minus our critical value of 1645 times whatever S is divided by root 25. So that's for your 90%. If we increase sample size, sorry, not 90%, I apologize. This was for n equals 25. If we increase our sample size to 200, our point estimate is the same. Our critical value is the same. But our standard error now is being divided by root of 200. So here, our S is being divided by 5. So let's say our S was 2, just to make things easy. 2 divided by the root of 25 is 0.4. 2 divided by the root of 200 is 0.14. When you make your sample size bigger, your denominator becomes bigger, which then makes your standard error smaller. So I made up this number. This 2 I made up. I made it up out of my head just to give you a concrete example. So what this is saying to you is, as n increases, standard error decreases because the bottom of your fraction gets bigger, and when your bottom of your fraction gets bigger, the divisor becomes smaller. So what will happen is that your interval is narrower. If your standard error decreases, then your margin of error also decreases. Because remember, margin of error is your critical value and your standard error. So this decreases, which means the whole thing decreases. So what is the biggest takeaway then from these notes that I have written here for us? Well, I'm going to write them down underneath the Garfield example. And that is the following. When you are looking at a confidence interval, critical value is affected by your confidence level. As your confidence level increases, so does your critical value. And you can see that here on your pink table. Standard error is affected by sample size. As you increase your sample size, you decrease your margin of error. So they are hoping that you would make those connections when you go through and try the problems like we did here. So if I go back to my quiz, so this is part 2, what affects critical value? Confidence level. What affects standard error? Sample size. Down here, when you increase sample size, standard error decreases. When you increase confidence level, critical value increases. And then I think that you can do these last two. Just keep in mind that if it affects one thing, it affects the other. So let me be more specific about that. If your critical value increases, then your margin of error increases. So because these two are being multiplied, if you increase critical value, that means margin of error also increases. If you decrease standard error, that means that margin of error also decreases. And the reason why is because these are being multiplied. So what affects this one will end up affecting this one. If there are any questions on this, please send me an email or ask me in class, because this idea here of how margin of error is affected by these things is pretty important. So we need to keep in mind they're separate. Critical value is affected by confidence level, and standard error is affected by sample size. But if we decrease this, then the whole thing decreases. And if we increase this, then the whole thing increases. And then our last quiz, part 3. I think question 1 is okay, question 2 is okay, and now I'm thinking, because I basically walked through this on our notes on page 609, I'm thinking now this problem is a lot more manageable. So hopefully that helps with the questions pertaining to the quizzes for lesson 61. Now, typically I would make a different video here, but I'm not going to make a different video because I'm hoping that some of you guys were able to fast forward through some of the previous stuff that we went through, so perhaps this video won't be as long for you. If you're feeling like, oh man, I need a break, take a break. You're fine. This video will probably end at around 40-ish minutes. We're 16 minutes in, so we probably have about 30 minutes of things to discuss. So if you're already like, okay, 16 minutes was enough, just take a break and come back to it at 17 minutes. Otherwise, we're just going to go over a couple of things in lesson 62, and I'm choosing to do those now because they are related to some of the things that we just talked about. So, going back to this problem here where our critical value was 2. Well, if I look down here on my table, down at the bottom where we have critical values, if I look at these values, none of them are nice. None of them are 2. They're all decimals. So where are these numbers coming from? Why do I have a 2 here, but then these numbers are different? The reason why that is because when we're discovering how a confidence interval is built, it's a little bit easier if we use the empirical rule. So notice up here, this is the empirical rule, and to keep things easy, we're using that. So we're using the idea that 68% of the data is within 1 standard deviation of the mean, 95% is within 2 standard deviations of the mean, and then 99.7% is within 3 standard deviations. So we're using the empirical rule, and it's a little bit easier because we just go 1, 2, 3. Well, remember how we talked about a while ago, what do we do if it's 1.25 standard deviations away from the mean, or 1.7 standard deviations away from the mean? This empirical rule then is not as helpful as it should be or as we need. That is where the standard normal table comes in, and you get all of these z values. The reason you have this z table is so that you can find the percent of data for any z-score. So let's look at this 95%, and let me just double check to see if this is a value. Yes. So skip ahead to 611, page 611, number 3. What truly is the critical value for a 95% confidence level? Because according to the empirical rule, it's 2. So based off of the easier empirical rule, the critical value is 2. But what is the true critical value? And to find the true critical value, you have to use your z table. So what this means is you are going to look for the z-score that matches 95% of the data being around the mean. So we know that it's going to be around 2. We know that it's going to be around 2. So you don't have to draw these flags yet if you don't want to. But we are trying to find the z-values that match this situation. A 95% confidence interval means that 95% of your data is within z amount of standard deviations. So this is the middle 95%. This is the middle 95%. We want to be able to say 95% of the data is z standard deviations away from the mean. According to the empirical rule, that's 2. But what is it truly according to our standard normal table? Well, if this is 95%, that means we have a leftover of 5%. But we have 2 tails here. We have 2 tails that we need to account for. So these 2 tails need to add up to 5%. So I take 5% and divide it by 2. That gives me 2.5. So if this is 95%, this is 2.5%. This is 2.5%. If I want to know the z that matches, if I want to know the z that matches this area, I need to go inside my table. So I need to go inside, sorry, I should write that lower. I need to go inside my z table and I need to look for (0.0250) because all of the areas inside your z table are written to 4 decimal places. If you need to know how I got that, I did 2.5 divided by 1,000. That gives me 4, I think I meant 100. 2.5 divided by 100. Yes, sorry about that. And then I have to add a 0 on the end. Because remember, this is a percent. So to change it to a decimal, I need to do 2.5 divided by 100. And then I just added the 0 on the end. Okay, so I am looking for 0.250. And there's 1 exactly. So it is at negative 1.96. Which ends up being very close to 2. So remember, the empirical rule is a very good estimate for these probabilities, but they're just an estimate. So the empirical rule says 95% of our data is within 2 standard deviations, but the true value, the true z-score is negative 1.96. Now, this is symmetric, which means that this z-value is going to be positive 196. And we can verify that if we want by going to the table 196, and that tells us that 97.5% of the data is to the left, which is what we have here. 95 plus 2.5 is 97.5% of the data. So once you find your negative z, your positive z is going to be the same except for positive. That is why for this one example, to make things easier, we use the empirical rule and we just use the critical value 2. But when you actually go and look at your critical values, none of them are nice numbers. And the reason why is because it's related to the standard normal table. And now if we look at 95%, we can see that the critical value truly is 1.960. So they want us to do the same for these curves. They want us to do the same for these. So for 80%, we're looking for the critical value such that 80% of the data is in the middle. So I'm not sure how accurate this is. I'm just doing this to get a visual of what I'm supposed to be doing. So this is 80%, which means there's 20% left over. 20% divided by 2 gives you 10% here, 10% here. So if I want to know the critical value, what I need to look up inside the z table I'm looking up 10 divided by 100. That gives me 0.1, and then I just fill in zeros as placeholders so that I can actually look inside the table. So I am coming to the table and I am finding the z value closest to 1,000. So those numbers are too big. So right here I have 1,003 and 985, so it's going to be this one. And I get negative 1.28. Negative 1.28. So I wasn't too far off on my figure. And if this is negative 128, that means this is positive 128. And I can actually check my answer here because these critical values are set in stone. So I can come to my pink sheet and I'm going to say, well, am I right? The critical value for 80% is 1.282, and we got 1.28. So we did this one correctly. So I'm going to do this last one with you, this 90%, and you should try 99% and verify that you get the right answer with your pink table, because this is one of your can you do problems. They do have you do one, and I don't remember if it's 90 or 80 or something. I don't think it's in your notes, whatever it is. So this time we're looking for 90%. I'm thinking it's going to be around 1.5 because it's got to be in the middle of these two, right? It's got to be right in, well, not right in the middle, but closer to 1.96. So I'm going to go with like halfway between the 1 and the 2. And I'm just doing this so I have a visual of what I'm finding. So the middle area is 90%, which means there's 10% left over. So this has to be 5 and this has to be 5. So I'm going to look inside the table. for 5 divided by 100. That gives me 0, 5, and I'm going to add on 2 placeholders. I'm looking for 0, 500. So it actually looks like it's right in the middle of these two numbers. This is 5 away, and this is 5 away. So it is between 164 and 165. It is right in between 164 and 165. So what you do to find out what the actual value is add these two and divide by 2. So 164 plus 165 divided by 2 gives us a critical value of 1645. I can double check that on my paper. So what were we doing? 90%, and we get the actual value this time, 1645. So what is it exactly that we are finding? Now that we have figured out where our critical value comes from, what exactly does this mean? So we can say with confidence that 80% of our samples will be within 1.28 standard deviations of the true value. 90% of our data will be within 1.645 standard deviations of the true value. And 95% of our data will be within 1.96 standard deviations of the true value. So you are now going to do 99% on your own. Oh, duh, look, I have the values down here, so you can use that to check your answer. Now, I'm not asking you a quiz question on this because really it's kind of silly to do that when you have these values down here. There's no way for me to know if you actually went through and drew this and calculated the percentages and did all that. So I would practice it and check my answer, and then just know in your you do have one question where it asks you to go through and do this, and I will not be giving you the solution for that. So make sure that any misunderstandings here, you get them cleared up, either by emailing me or watching this again or asking in class. So this is where critical value comes from. We're skipping 612 and 613, and we're going to do some problem solving with our confidence intervals. Now this is specifically related to confidence intervals for P. So this is specifically for confidence intervals for P. So the last thing we're doing in this video is page 614 and 615. To increase business, the owner of a restaurant is running a promotion in which a customer's bill can be randomly selected to receive a discount. When a customer's bill is printed, a program in the cash register randomly determines whether a customer will receive a discount on the bill. The program was written to generate a discount with a probability of 0.2 or 20%. So 20% of the bills will be given a discount in the long run. The owner selected a random sample of bills and found that only 15% of them received a discount. A confidence interval for P, the proportion of bills that will receive a discount in the long run, is our point estimate, which was 0.15, plus or minus a margin of error of 6%. So I'm going to write down right here what I know. We're hoping that the probability is 20%. So we're hoping that P is 0.2. We have a P hat of 0.15 and a margin of error of 6%. So our program should be giving 20% of our bills, 20% of our customers a discount. We take one sample and get that 15% got a discount. Our margin of error is 6%. Does it tell us our confidence level? No, this does not tell us our confidence level. So let's actually find our confidence interval. Our lower bound is 15% minus 6%. So that's going to be 9.099%. And our upper bound is going to be 0.21 or 21%. So our confidence interval, the true value of P, can be any percent from 9 to 21. So 9% to 21% is a plausible value for true P. Does the confidence interval provide convincing statistical evidence that the program is not working as intended? Well, if the program is working as intended, P would be 0.20. Well, is 0.20 in our confidence interval? Yes, 0.20 is a plausible value for true P. So is this convincing evidence against that? No. Because the desired value of 0.20 is in the confidence interval. So similarly, 0.20 is a plausible value for P. We would have convincing evidence if 20% was not in our interval. Does the confidence interval provide convincing statistical evidence that the program generates the discount with a probability of 20%? Justify your answer. So we have to be really clear about what they're asking us here. So they're saying, does this give us evidence that the program is working as intended? Is this evidence that supports the claim? And remember, we no longer say our confidence interval or our dot plot supports the claim. We're only looking for evidence against the claim. So is this convincing statistical evidence that the program generates a discount with a probability of 20%? No. P of 0.20 is one of many plausible values for P. P could be any value in the interval. So P could be 9%, P could be 10%, P could be 11%. So this is not evidence to prove the claim or support the claim. This just tells us that it could be working properly. We do not have evidence against the claim. We don't have evidence to prove the claim is true, but we don't have evidence against it, so it could be working properly. So no, we don't have evidence against the claim, and no, we don't have evidence to support the claim. All we can say is the program could be working as intended. Okay, now this second question requires me to walk through a fair amount of math for you. So I'm going to give you the takeaway, and then I'm going to work through the math with you, and you can choose to fast forward if you so desire. So a second random sample of bills was taken that was 4 times the size of the original sample. In the second sample, 15% of the bills received a discount. So P hat stays the same. Sample size is now 4 times as big. So determine the value of the margin of error based on the second sample of bills that would be used to compute an interval for P. So they're saying we need to adjust this margin of error of 6%. So what the math is going to show you, what the takeaway is, you will adjust margin of error by 1 over the root of f. Well, what is f? The factor that you adjust by. So if we're going 4 times as big, we're going to say f is 4. That is the factor by which you increase or decrease your sample. So that means that our new margin of error is going to be 1 over root f multiplied by our old margin of error. This is going to be 1 over root 4 multiplied by 0.06. So your new margin of error is 0.03. We cut the margin in error by half. So we've seen this before in the sampling distribution unit. Now I'm going to work through the math up here. If you are not interested in the math and all you're going to do is memorize this formula, by all means, fast forward. If you want to see the math, then hang tight. So we know margin of error is our z-score, our z-critical, multiplied by our standard error of p hat. So that means that this is our z-critical multiplied by this big old ginormous formula. But we want to adjust n by f. We want to adjust n by f. So we want to adjust n by a factor of 4. Then sorry, I just don't want to use red anymore. Margin of error is our Z critical multiplied by P hat 1 minus P hat all over F times N. Because remember, we're adjusting our sample size by a factor of 4. Okay, well, this is the same thing as our Z critical multiplied by the root of 1 over F times the root of P hat 1 minus P hat all over N. So all I'm doing is pulling out that factor of 1 over F. And that's mathematically sound. I am allowed to rewrite this radical as this radical. So let me highlight that so that you can see. This turned into this. Okay, well, if I just rearrange things a little bit more, I can put the root on the front, 1 over F, and that can all be multiplied by Z critical with the big root. But this is our old margin of error. This is just the margin of error that we already have. So, MOE new is equal to root 1 over F times MOE old. These two things are the same. This is just the same thing as 1 over root F times your old margin of error. And that's what we're doing here. 1 over root F times your old margin of error is going to give you 3%. I don't think that they'll ever ask you to figure this out on your own. Well, actually, this is a free response from 2015. I'm not sure if in order to get full credit, you needed to be able to show this math. I know for sure this would at least give you partial credit. You probably would get full credit if you made these statements. If you clearly stated that you know that the new margin of error is the old margin of error adjusted by a factor of 1 over root F. Why did I write this like time? So this is a previously released free response problem. Okay, 10 years later, we can actually answer the question. Based on the margin of error in Part B, what do you conclude about whether or not the program is working as intended? Okay, well, now our confidence interval is 0.15 plus or minus our new margin of error. So this gives us a confidence interval with a lower bound of 12 and an upper bound of 18. So based on this second sample, what do you conclude about the program working as intended? Now remember, working as intended is 20%. The program is not working as intended because 0.20 is not included in the new interval. So P equals 0.20 is not a plausible value. Actually, I should say so. 0.20 is not a plausible value for P. So with a sample, with the original sample, we don't have evidence against the claim. The machine could be working properly. If we take a sample 4 times as big, though, if we look at more samples, we now have evidence against the claim. This is why having a large sample is always better, up to a point. Remember, we can go up to 10%, so you want to try to go as big as you can, because notice here, we have evidence against the claim now. Okay, last set of problems, and they're quicker. The last set of problems, or the last problem really, is quicker than this last one. Remember, if you need a break, take a break. If an hour is too long for you, take a break. This last problem, we should end right at about an hour, so we're getting there. A CNN poll asked N equals 65 random residents in a large city for their opinion about politics in the United States. Do you think that the last national election was crazier than the other past elections? The confidence interval that results is 0.479 to 0.681. So I'm thinking that this represents the people that said yes. And they're referring to the election of when it was Trump and Hillary. So this was 2016. So first question, what is the point estimate for this interval? So remember, this is P hat, because these problems all have to do with confidence intervals for P. Well, it's going to be our lower bound plus our upper bound divided by 2. So lower bound plus upper bound divided by 2. You plug that in and you get 58%. Calculate the standard error for this interval. Okay, well, standard error of P hat is P hat 1 minus P hat all over N. So 5/8 times 4/2 divided by 65, because in the problem they tell us N is 65. So I plug that in and I get 0.0612. Use your knowledge about what makes up the margin of error to determine what level of confidence must be used. So if we want to know our level of confidence, we also need to know our critical value. Okay, so it says use our knowledge of margin of error. Okay, margin of error equals our critical value multiplied by our standard error of P hat. Okay, we know this, or we have this. We can find this. How do we find this? We have a formula. So margin of error is your upper bound, 681, subtract your lower bound, 479, and we divide by 2. That gives us a margin of error of 0.101. Okay, so now let's fill in all of the values that we have. 0.101 equals our critical value multiplied by our standard error. Well, if we want to know critical value, then we just need to divide both sides by 0.0612. So our critical value is equal to 1.65. And really, in this problem, I should be using Z. It's called Z critical. So our Z critical, or our Z score, is 165. So I'm going to go to my pink table, and I'm going to find the one closest to 165. That's 90%. So our confidence level was a 90% confidence level. So we found this by solving an equation using critical value to determine confidence level. So in this video, we went over the most commonly asked questions from lesson 61. Then we tied that into this idea of where do these critical values truly come from? We talked about margin of error and how it's related to your critical value and your standard error. We did some problem solving related to that. And we talked about having evidence against the claim. There is no homework at this point that goes with this. What you should do now are the questions that go along with this video, and then as usual, if you guys are struggling with anything, email me or ask me in class. Otherwise, love you. Good job hanging in. Love you. I was going to tell you that I'm not sorry that this is so long, but I am a little bit sorry that it's this long. So I try to keep the videos short, but when they're longer, you guys are in control. Take breaks when you need them. Fast forward when you need to. Proud of you for making it through, and I know that it's not always fun, but good job for hanging in if you did. Okay. Love you guys.